So I may be tempted to stop and talk to you anyway. I have a weakness that way, but let me start by putting it all on the table. By the way, these slides were produced by Tom Mitchell as part of his book, the textbook. So they dovetail very closely with the book. You can see they reproduce some of the tables and graphs and pictures from the book and summarize the important points from the book. So they're a good way of reviewing the material in the book. And I don't know if I mentioned it. If I did, maybe I didn't mention enough. The official material for the course, what you really need to understand, not just for exams but for life, I guess, is a combination of what's in the textbook and what's in the lecture. So over the years my lectures have diverged more and more from the textbook, not conceptually they're the same, but I don't quite follow exactly the textbook, and every now and then I branch out into completely different things like information theory or philosophy or whatever it is, but it's still important that you read the relevant chapter in the book and make sure you understand all of it and bring the ideas to class and ask questions and so forth. It's all fair game for you and for me. Okay, so this is from the slides. And when are neural networks most useful? Well, when the input is high dimensional and or real valued. Typically neurons take continuous values, artificial neurons take continuous values. The output could be discrete or real valued. Discrete output means that the top neuron at the very end could be a threshold neuron, or it could be a continuous one but you impose a threshold later, and there could be more than one output. One very common trick which I mentioned before is how to use a neural network for classification. If you want to classify into k different outputs, you produce you want to classify into k different categories, so every input must be classified into exactly one of them. The standard way for doing that is to have k outputs, one associated with each category, and interpret the output as winner take all, meaning whichever output has the highest value is declared the winner, and that's the category you assign to your input. Okay, it's a standard way of doing it. If you do it right, it is possible to actually derive a posterior distribution over the output, namely that the relative strength or activation level of the k different outputs is proportional to how likely they are to be the correct category. So this is generalization from just classification where you choose one category to a softer kind of classification where you say, well, it could be this with 80% chance, or this with 5% chance, or this with 7% chance. If you give a whole distribution called posterior distribution over the possible categories. Output can be discrete or real valued. Output could be a vector of values, possibly noisy data. Neural networks are very good with noisy data. I'll talk about it in a minute. It's good to use a neural network because, especially when the form of the target function is unknown. That is actually very important. That means when you have no idea what the bias should be. Right? If you have some idea of what the form of the answer should be, it should be a conjunction of things, so it should be, should only involve 2 or 3 variables or whatever, then you need to tailor a machine learning technique that has that kind of bias. If you don't know what to choose a neural network. Why? Because it's a universal approximator. It can approximate any function. It doesn't mean it doesn't have a bias. We'll talk about it in a minute. It does have some soft bias, but it doesn't have a hard bias, and if you make it large enough, you can represent just about anything. Human readability of result is unimportant. Why is it there? So when you train a decision tree and you finish training it, you look at it, it makes sense. You can look at the question at the root and say, the most important thing to know is whether temperature is high or low. And if it's high, I need to check humidity. And you can sort of tell yourself a story of what the network is doing to reach its decision. The most important explanation is at the top, at the root, and then one layer down, maybe one level after that. Once you go below that, it gets to be a little more difficult and not so crisp. But nonetheless, there is a coherent explanation that you can glean from looking at the decision tree. Same is true for several other techniques. For neural networks, it's not so easy to see what the neural network is doing and how it's doing what it's doing. There are some techniques for doing that. You need to look at the weights, and you need to have special visualization to look at a large number of weights and try to figure out from the weights what each neuron is computing. And neuroscientists actually do that in the brain. They try to figure out what's called the receptive field of any given neuron. The receptive field of a neuron is the set of stimuli that cause that neuron to fire. So in an artificial neural network, the receptive field would be the set of inputs that would cause that neuron to go over that sigmoid hump. So if you have all these characteristics, you're a prime candidate for neural networks. Question?
When would you use a decision tree and not a neural network?
When will you use a decision tree and not a neural network? That's a very good question, and to speed things up, I'll just give you the answer rather than pose it to other people. You will use a decision tree when you suspect that the right explanation has a form that's easily represented in the decision tree, which means, in the case of decision trees, that it depends on a small number of inputs. Even though you may have 100 inputs, you suspect that any one answer depends on only 2 or 3 or 4 of them, and that the dependence is somewhat binary, not linear, but from here on it's like this, from here on it's like that, roughly binary. You can always approximate things, and that depending on the value of some variables, different variables might be important. So if it's very hot, you care about humidity. If it's cold, you care about wind. Okay? The examples you see here are 3 from thousands. There are lots and lots of applications where neural networks proved useful. The speech recognition one I showed you last time, that's the phonemes, the vowels. I can tell you about another very famous one. It was done actually by a friend of mine, a guy named Dean Pomerleau, who was here in graduate school with me at the same time, and he worked on vision. And he worked with a group of people who were working on the autonomous vehicle, the car that drives itself. And before he joined them, they used traditional non-neural network techniques for analyzing the input. So they had a car and they had a video camera that was taking snapshots of the road every half a second or so. And then they had heavy-duty computers, at the time it was heavy-duty, it was the late 80s, to analyze that image. I think it's a black and white image or grayscale image, and try to find lines in it and identify where the road is. And they were doing fairly well. And of course, the better you do in figuring out where the road is so you can control the steering wheel, the faster you can allow yourself to drive. And now they were nowhere near a person, so they would drive at the speed of about 4 or 5 miles an hour, which is the speed of walking. Okay? He threw away all the algorithms that they developed over the years and just took a lot of training data and trained a very simple neural network. I'll show you the neural network that he trained. Here's the car. Oops, I'm giving you the punchline, but never mind. Here's the car. Here's the neural network. This is the retina, so to speak. This is the input. The input is a 30 by 30 sensor input. So there are 30 by 30 pixels here with some grayscale. There's a single hidden layer of 4 units. When I saw him working on that, I thought he was crazy. What can you do with a single hidden layer of 4 units only? And then from that you have 30 outputs, and the 30 outputs are interpreted the way I mentioned to you before as a winner-take-all. Namely, he looks at for any given set of inputs, he propagates the inputs through the network, looks at the activation level of the outputs, chooses the one that has the highest activation level, and that's the answer. And the answer corresponds to whether you should tilt the steering wheel all the way to the left, a little bit less, a little bit less, a little less, center, or all the way to the right. Okay, so it's just one of 30 answers which direction you should tilt the steering wheel. He used a supercomputer to train this network. How many weights are in this network? Well, the dominant part is the matrix from here to here. There are 900 units here and 4 here. So it's 900 times, 4 times 4. So 900 times 4, it's about 4,000 maybe weights the whole network. He used, thousands of input-output examples. Maybe more than thousands, maybe tens of thousands. Very easy to get those examples. All he has to do is mount the camera on the car, drive it around. He did it on Flagstaff Hill, on that little windy road there, and just collect snapshots and annotate them with which direction you need to turn the steering wheel. So you have input, output, input, output. Repeat 10,000 times. When he is done training it, this is an example of trying to figure out what the network is doing. So this is a kind of a receptive field of one of these 4 hidden units. So it shows the strength of the connections for any one of the input units to, let's say, this one. Black is negative, white is positive, I think. The size of the black or white depicts the magnitude of the weight. What it looks like this receptive field is doing is it's looking for something that looks like this. And it evaluates every picture with regard to how similar it is to something that looks just like that in that position. And if there's a picture, there's an input that looks exactly like that, that neuron will fire like crazy. But if there are pictures that look somewhat similar, it would fire still not quite as high, but that high. These things are also known as Hinton diagrams. Jeff Hinton was a faculty member here at CMU for a while. He's in Toronto now. He made a lot of contributions to neural network theory. Still does. This is also a Hinton diagram of the same unit, but now of the outgoing weights. So you can see that when the neuron sees something that looks more or less like this, it fires, and when it fires, it tends to activate the turn to this side. And if that doesn't make sense, I probably have my interpretation of black and white incorrect. But the idea is that it makes a meaningful decision which direction to go. And the amazing thing to me is that with 4 different very simple pattern matchers that are then combined together, you can make a very reliable decision. And the story goes that after Dean joined the team, and a year or 2 later, when he had his neural network trained, they were able to speed up the autonomous land vehicle. They call it Alvin, autonomous land vehicle in a neural network. They were able to speed up Alvin from 4 or 5 miles per hour to 10 miles per hour, 15 miles per hour, 20 miles per hour. And every time they speed it up, that means that it got more accurate and fast. Well, of course it was very fast, because neural networks are very fast to use. They're not fast to train, but they're fast to use. And then 20 miles per hour, 30, 40, 50. When they got to 60, it became a bit of a problem. What do you do if you drive a car at 60 miles an hour in a 55 mile an hour zone and the policeman stops you? Who gets the ticket? I mean, but the real nice end of the story is that they had a victory parade of sorts. They had a car, what do you call it, ride, all the way across the country from Washington, D.C. to San Diego, passing, of course, through Pittsburgh and a few other places. And their car did it with no driver 99-point-something% of the time. The only places where they had to have a driver was when they went through tunnels and some other unusual conditions the network was not trained for. And I'll bring you my T-shirt that shows commemorates that event. And the slogan is, I don't know if you remember, or you were too young. There used to be a thing, Hands Across America. People link Hands Across America. Have you heard about that? So their slogan was No Hands Across America. So this is a classic success story of neural networks. Something that was originally done with a lot of thinking and a lot of analysis of the domain. And I'm not poo-pooing that. I think you need to analyze the domain. But neural networks have the ability to take something that is difficult to program explicitly, difficult to do by analytic methods, and just throw a ton of data on it, and with a surprisingly small architecture, just throw backpropagation at it, and when you're done, it does a fairly good job, surprisingly good job. And they went on to make it work better. This was done in single lane, they made it work in 2 lanes, then they made another network that told you whether you're in a 1 lane or 2 lane situation, and there were all sorts of ways of expanding that. So they went up to 70 miles an hour on highways. Backpropagation is very slow. Why is it slow? Do you remember the algorithm? You have to propagate the error back. You have to, for every iteration, you have to iterate over all training examples. Right, so first there's a big loop over making steps in gradient space. Then inside each one of these loops there's a loop on all the training examples. Then for each one training example, you have to propagate the value of the training example through the network. So you have to basically touch every neuron in the network and sum every weight in the network. Then when you get to the end, you have to propagate back the error signal, which again has to touch every neuron and sum over every weight. So there are like three deep nested loops in there, and nobody tells you how long gradient descent will take, right? It depends on your step size. So if your step size is too small, it may take forever. If it's too large, you may not get a good local minimum. So there's a bit of an art there, but it is not uncommon that somebody trains a neural network for months. Hopefully you want to train it for a few minutes or hours so that you can tweak it and try different things. One of the nicest things that was shown for neural networks was shown by Geoff Hinton, again when he was here, and it was that the neural network is able to learn meaningful internal representations. So if you look back at the Alvin example, you can think of all the wealth of information that can be expressed in the input passing through a bottleneck of just 4 units, 4 hidden units. Right? So there's a tremendous amount of information here if you think in information theory terms. There's a tremendous amount of possible information here, and all of that gets squeezed into the state of these 4 units. So there's a bottleneck there. And it's interesting to think about what representations develop at the bottleneck. So what Geoff Hinton showed is that when you force a network to compute something going through a bottleneck, it discovers meaningful representations. Why are they meaningful? Because they're forced to convey all the important information important for the output, and at the same time they're forced to be very compact. Okay? If you force someone to say something in very few words, and it still has to convey the information, what they're going to say is going to be quite meaningful. Right? Whereas if you allow them to blabber on and on, it might contain the information you want, but too many words. Or if you don't require that the output would contain anything, then it's very few words, but it's not meaningful. But a combination of, you got to have enough information left to produce the right output, but you got to do it in very few bits, is very powerful. And he gave a very nice demonstration from a very simple synthetic network that was forced to basically learn the identity function. So this is, instead of being from bottom to top, this is left to right, but still you have here, oh, I brought something with me. You have here inputs, 8 inputs, 3 intermediate units in a single layer, and 8 outputs. And the network was taught a very simple thing. 8 input-output pairs, and the input is the same as the output. Basically you have to reproduce the input, only for these 8. Now, can this be learned? Can you learn this function in a neural network using only 3 intermediate units? The computer scientists in the crowd, which hopefully are the majority, should say, yeah, you just use a binary representation, right? As an engineer, you can immediately say, well, you have 8 possible inputs, you have 3 units in there, we can use the binary representation. And that is exactly what the network learned. It discovered binary representation. After training it with backpropagation, here are the values of the hidden units that corresponded to each one of the inputs. And you can see that this is high, low, 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 high, low, etc. Of course, it didn't do it in any neat, organized way. It just learned whatever it learned. You can also do interesting sort of either post-mortem or diagnosis of a network as it learns things. Here is an example for that specific 838 network of the sum of squared errors over all the training examples of each unit as a function of the iterations of backpropagation. So you see it took about 2,500 iterations of gradient descent steps for the network to fully learn the input. And you have 8 curves here. These are the 8 different output units. And you see that different output units learn at different times how they're supposed to behave. Okay, so when the sum of square errors, this is the sum over all 8 possible inputs. When the sum of square errors of a specific output unit drops, that means that output unit finally figured out how it's supposed to behave for each input. Okay? And you see that they learned it in a very nonlinear way. They got it all of a sudden. Just one unit figured out what it's supposed to do, so to speak. This nonlinear behavior is due to the nonlinear gradient. We have this sigmoid transfer function, and the backpropagation pushes you in one direction or another, and once you get to that interesting twist, you get pushed pretty fast. But this one and this one learned it quickly, and then this one took a while to figure out what it needs to do. Yet another way of looking at the same kind of process is, this is the hidden unit encoding for a specific input. So this is one possible input, and these 3 represent the 3 hidden units. And the way this graph was drawn is, for any particular iteration, you freeze the weights, you introduce this input, you propagate it forward, and you collect what the values of the output units are. And of course, once the network finished learning, the outputs were low, high, high, as you saw in the table. But you can see that when you start, the network is not sure what to do in response. How do you... basically, this is a step where it's figuring out which 3-bit binary code to use for which input. And it made a quick decision on this one, and then here they said, okay, I'll send this one up and this one down. Let's skip the rest. Okay. What is the bias of a neural network? Darn, you got to think again. There's no one right answer. I mean, there are many ways of thinking about it, characterizing it. So, were you raising your hand?
The bias is present in the training data.
The bias is present in the training data. Okay, so what you mean is that whatever you train with, the solution will gravitate towards sort of mirroring that relationship. It's true, but I wouldn't call it the bias of the neural network. This is true for any machine learning problem, and it's not what we call bias. It's a real phenomena, but it's not what we call bias. What we call bias is something that is characteristic of either the representation, that's the hard bias, or the algorithm for choosing. So if you think of all the solutions that correspond to the training data, or that are consistent with the training data, does the algorithm or the representation push you towards some of them at the expense of others? Please.
Either the step size or the random starting position.
If I understand you correctly, you're saying that the step size and the random starting position help determine where you end up, so they influence the choice of which function that's true. Okay, so again, that doesn't exactly answer what I wanted, but it does give me useful information. You're saying that at least the step size and the starting position have an impact on sort of favoring some solutions over the others. True? Please?
The chosen topology.
I'm sorry?
The chosen topology.
The topology. Yeah, topology network. So all this is true. Let me rephrase the question. What kind of functions are more likely to be chosen by a neural network in general over other functions? What functions do they tend to favor as solutions? That's what I meant by soft bias. Let me help you along the way. Suppose you start with a neural network that has very small weights. Very, very small weights, very close to zero. What kind of function does it compute? Sorry? Linear function. Why?
Because the sigmoid function, when x is approaching zero, is just like linear.
Right, very true. So, if the weights are very close to zero, then the sum of the inputs, the weighted sum of inputs to anyone from the inputs to the first layer is very close to zero. Right? If the weights are close to zero, if the weights are about zero, then the product of the weights and the input is also about zero. And this is what comes as input into our transfer function. And our transfer function looks like this, but around zero it can be approximated by a straight line. The nonlinearity comes in here and here. But right around zero it's pretty straight. So the transfer function is pretty straight. So any one unit acts as a linear unit, more or less. And we already know that linear units, when combined together into a network, compute a linear function. So if you start a network with very, very small weights, it is basically computing a linear function. If they're really zero, then it's computing zero. As you train a network, some of the weights grow positively and negatively, and as a result the total net moves away from this point to somewhere on here, and you start introducing nonlinearities. So as you train a neural network, you move away from linear to some distorted version of linear. And that distortion can become more and more distorted as you train more and as long as you have enough units. So one answer for bias is that, at least the bias of the backpropagation training, given that you start with very small weights, is start from linear and then distort it as needed. Another way of characterizing bias is that neural networks always calculate continuous functions, right? I mean, may not have thought of it much, may think it's trivial, but decision trees don't compute continuous functions, right? They have hard edges. Neural networks always compute continuous functions, and the smaller the weights, the more continuous they are. When the weights, if some of the weights are very, very large, you can create very strong nonlinearities. It's still continuous, but it could be very curved. So one of the reasons, I think, this is more of a hand waving, one of the reasons neural networks are so useful is that they can form any shape. If you talk about classification, or if you talk about function mapping, producing an output, they can approximate any reasonable function. But they do it by starting from a very simple linear surface, and then they introduce whatever distortion is needed to the linear surface to minimize the error. That's the nature of the bias. Basically start with something simple and distort it as needed. It seems like a very reasonable bias. Okay, can neural networks overfit? Yes, no, show of hands. Can they overfit? Yes, they can overfit, absolutely. Here's a classic example of overfitting. This is the training set error as a function of weight updates or gradient descent iteration steps. And this is the parallel error computed on a validation set. And you see in the beginning it goes down. The training set error will always go down. This is a feature of gradient descent. As long as the step size is small enough, it will always go down. This corresponds to growing a decision tree, and the error always goes down. But the error on the validation set can start going up, and this is, by definition, the onset of overfitting. So one thing we could do to avoid overfitting is keep some data out, use it as our validation set, and as soon as the error starts going up, or maybe even as soon as it levels off, stop and say, okay, this is the network I'm going to produce. I don't want to be here. This looks great, but it's really bad. I want to be here. Well, this is just a little bit worse than here. A little caveat, sometimes the validation set error will fluctuate. So here's an example where it reaches a minimum, starts going up, and if you decided to stop here, stop training, that will not be so good, because if you continue, you go over the hump and you continue to go down. So an improvement to the previous idea is to train the network to saturation, as much CPU as you can afford, until the training error reaches minimum. And then calculate the validation set error all along the way and choose the lowest point. So don't stop the first time it bottoms up. Give it a chance to keep going down. Okay, we talked a lot about the different types of transfer functions that could be used, and we settled on the sigmoid, and indeed this is by far the most commonly used transfer function. Because it is continuous, it is nonlinear, and it is differentiable. There are others that can be used. I'm not going to talk about them, but we didn't talk much about the error function. The error function I used is a simple quadratic error function. It was easy because the gradient is very easy to calculate. Derivative of a quadratic is very easy. It also makes sense in many situations. I mentioned to you when you expect there's some noise, a Gaussian or normal noise, as quadratic error is a natural measure to use. But there are others, and let me mention some of them. Suppose you prefer to build a network that has small weights. For a variety of reasons. Could be because you're going to implement it in hardware and it's hard to do with large weights. I don't know. Could be because you believe that the right bias for the solution is network with small weights. Remember, the small weights correspond to being closer to linear. So you don't want solutions that are highly nonlinear, that are highly curved and weird shape. You want something that looks fairly smooth. So you're looking for a solution that on one hand does well on your training data, minimizes the standard error of the training data, but at the same time you want it to have small weights. You have two goals here, two separate goals that you have to somehow weigh against each other. This should remind you of the examples I gave you with fitting a polynomial. Remember, you could fit a 7th degree polynomial perfectly, or a 2nd degree polynomial with some error. We did that in class, didn't we? So again, you had two goals there. One is to fit the data as well as possible. The other is to use as simple a model as possible with lower degree. So here, simple model corresponds to low weights. There's a way you can optimize these two things together using the exact same formulas and the exact same wave propagation, and that is by adding a term to your error function. A term that penalizes, in this case, large weights. This idea of lumping together into one objective function, one optimization criterion, everything we care about is called regularization. Because it is used to regularize functions, to pull them towards something more regular, more smooth. So in the case of large weights, here's your error, one possible error function. There's one component that is familiar to you, that's this component. And then there's another component that is the sum of the squared of the weights. So it penalizes large weights in a quadratic way. You could penalize them some other way. So this is the sum of the square of the weights over the entire set of weights in the network. This gamma is a weighing parameter. It tells you how much you care about reducing the sum of the weights versus fitting the data, right? That's what allows you to compare apples to oranges. It's the exchange rate of apples to oranges. So the important thing is the big regularization idea. It doesn't have to be sum of weights. It could be something else. But if you care about several different aspects of the solution, represent each one by some error term, lump all the error terms together with some weights that do the exchange rate between them, that's up to you, and then you can do gradient descent in this combined error surface. Here's another example. What does this do? This is a little harder to read. So the error here is defined as sum over all the training examples, sum over all the outputs of, first of all, a quadratic term of the error, the standard error, the disagreement between the actual output and the desired output, squared. So this is the standard error measure. And now we're adding a component which is related to the difference between the derivative of the output with regard to the input and the derivative of the same output with regard to, what is different here? Oh, I'm sorry, this is the desired output, this is the actual output. So you're comparing the way the actual output varies with regard to the input, how the input changes it, to how it changes it in your current network. So what you're, I'm not sure I fully understand that, because for this derivative to be meaningful, this has to be a continuous function. But the general idea here is that you care about the sensitivity of the output to the input. Namely, you don't want a solution that gives you the correct answer on your specific training examples, but if your input changes a little bit, the answer changes dramatically. Because you believe that the answer should change slowly with slow changes in the input. So you can explicitly represent that with some derivative of the output with regard to the input, but I don't fully understand this. I have to go back to the book. It comes from the book, you can look at it yourself. Okay, so there's so much for regularization. The last tidbit that I want to tell you about neural networks is I mentioned to you that there can be recurrent neural networks. Namely, neural networks whose underlying graph structure is cyclic. You can have loops. That is definitely the case in the brain. In human brain and animal brains, there are lots of loops. Because there's projection from one part of the brain to another, and then there's feedback from that part back to this one. And loops complicate things. On the positive side, loops allow you to calculate things that you could not calculate without loops. Much more complicated things. They also introduce an explicit dependence on time, because when is the calculation considered terminated? I mean, there's some juice that's flowing in the network in all directions, and you can also think of recurrent networks or cyclical graphs as doing calculation that is continuous in time. There's continuous input coming in, and there's continuous output going out. So there's a lot. It's no longer a static input output. It's something a lot more complicated than that. Nonetheless, backpropagation for recurrent networks has been worked out. So there is an algorithm, just like backpropagation with some modification, that can be used to train a recurrent neural network. Again, it's subject to the standard caveats that it'll find the local minimum, but it can be done. One way of figuring it out, one way of thinking of recurrent networks, and one way of deriving the algorithm is by taking a recurrent neural network and making copies of it in time. So there's the neural network as it is at time t, and then at time t minus 1, time t minus 2, time t minus 3, and instead of having it connected in a loop to itself, you have it connected. The output of time t minus 1 goes as input to time t. So here's what it would look like. This is a standard feed-forward network. This is a recurrent network, and what's recurrent here, for example, is that this unit here, which got input from these 4 inputs, serves to feed the input for the next timestamp. So these are still inputs, these are still hidden, and this is still output. But this hidden unit, which was calculated as a function of the value of these at time t, becomes the value of one of the inputs at time t plus 1. So if you unfold it, here's the network at time t minus 1, and it's a standard feed-forward network, and this unit is connected to the input unit of the same a different copy of the same network at time t, and this one in turn is connected to a copy at time t plus 1. And by doing that, you can think about it as a feed-forward network. You can figure out the standard backpropagation rules for feed-forward network, and then recognize that this weight must be the same as this weight, must be the same as this weight. It's really the same weight. So you have to do what we call tie the weights together. Namely, in your backpropagation algorithm, you say these three weights must be the same value. So you take the value the network assigns to them and average them and give it back to all of them. This is actually a general technique that you should know about, not just for recurrent neural networks. Sometimes you believe that the formula solution should be such that it's symmetric. Or for whatever other reasons, maybe you don't have enough data, you can't afford to have too many parameters, you want a whole set of weights to have the same value. You can enforce that in backpropagation by running the starting by randomly seeding, then taking the whole weights that you want to be the same value and averaging the value and giving the average back to everybody. So think about it as a socialist commune where everybody goes out and gets paid, but when they come home everybody has to put it into a pot and then you split it evenly. And then you go through a backpropagation step and you get different delta weights, different changes in the weights based on the algorithm. But again, you take all these changes, put them in a pot, average them, and then force everybody in that group to have the same correction. Any questions about neural networks? Please.
How do you know how many hidden units to include in your neural network?
Yeah, that's a wonderful question that does not have a mathematical answer. I mean, there are many answers. People have worked. This is the biggest question in neural networks is network topology. How big of a network? You know how many inputs you have because that comes from your problem. You know how many outputs you have, that comes from your problem definition too. But what's in between you don't know. You don't know how many units to use. You don't know how to arrange them in layers or not, and if in layers, how many layers, and generally how they should be connected. You don't know any of that. So the short answer is we don't know. Now there's a longer answer that we should talk about a little bit. What happens if you use too few units? What might happen?
The answers might become compressed because there's not enough distinguishing between, there's not enough machinery to distinguish between outcomes.
That's good. In my favorite terminology, I would say that the hard bias is too strict, too strong, the representational power is too weak, and the correct solution might not be in there. So if you have a very small network, the set of functions that it can represent, as you vary the weights, is small. And it may not contain the correct one. How will you notice it? What will be the symptoms? So let's say you have 4 inputs and a single hidden unit and a single output, and you're trying to learn some very complicated function. Let's say you have 100 inputs and 1 or 2 hidden units and 1 output, and you're trying to learn a very complicated function of these 100 units. What would happen?
Well, practically the error might be too large. When you actually finish learning it,
right.
When you converge to a solution, the error is really large.
Right.
And that would say maybe it's the wrong number.
Right. You will not be able to learn, even over the training data, you will not be able to reduce the error rate to 0 or even close to it. Tom?
If you have enough nodes, should you expect 0 error?
That's exactly where we're heading. So if your network is too small, what might happen is that the solution might not be there. It may not be representable in that network. And what you will see is the training error doesn't go to 0 or even close to it. If you have a network that's too big, what would happen? So you're trying to learn some function from 5 inputs to 1 output, and you allow yourself 2,000 intermediate hidden units. Will the training error go to 0? I see yes and I see no. Can somebody explain?
Are you overfitting in that case?
You may be overfitting. Okay. Somebody else? Please.
So we already kind of said that neural networks work better when you have the minimum amount of units that you need for that one example.
Work better in what sense?
Work better as in perform the job much better. Like you kind of showed that example with the learning the 8 numbers.
So the example with the 8 numbers was 838. Suppose I didn't have 838. Suppose I had 808. Will the network not be able to learn the mapping? Not optimally. Please.
It will learn it, but it's not very
You will learn it, but not be very meaningful. Dan?
Probably it won't use 97, but
It won't use all the resources it has. There's just a few of them. Please.
I think maybe some of the weights are near zero.
It will be near zero. So that's similar to what Dan was saying. Okay. Any other comment? Any more suggestions?
Will it take too long to learn?
Which one will take longer to learn? 838 or 808? If you're learning the same set of 8 examples. So the same training data, which consists of 8 examples of these 8 bit vectors that are mapped to themselves. Same algorithm. The only difference is you have 3 units as a bottleneck, or you have 100 units in the middle. 100 is, when I say take longer, I'm sorry, let me qualify that. Which one will take more iterations of the backpropagation algorithm? Because the one that has 100 intermediate units has many more weights, so each iteration might take more cycles, more CPU cycles. But I'm not concerned about it. I'm concerned about number of steps, gradient descent steps. Okay, which one will take more steps? The 3 will take more. Anybody wants to disagree? So the answer is, when you have so many hidden units, you have huge representation power, and there are many possible solutions in that space. As opposed to the other extreme, when it's too narrow and you don't have any solutions. When you have 100, when you have not a bottleneck but a huge opening in the middle, you have a very large representation power, and therefore there are many solutions, and therefore it's very easy to find some of them. And they don't involve much squeezing and nonlinearity. So the network will converge much faster if you have 100 intermediate units. Unfortunately, then your intuition, I think, is incorrect, or at least it disagrees with my intuition, that it will not use 97% of the units. If the network were an engineer, a human engineer, it would say, I don't need 100, I'll keep 97, I won't touch them, and I'll solve my problem using just 3. But what actually happens is the network doesn't know what it will need, and the gradient descent pushes in the weights of all the intermediate units. So eventually all of them get involved in some small smeared way in the answers. On the other hand, the solution is fairly robust, probably, in that if you kill 2 or 3 of those 100 intermediate units after the network has been trained, it will still probably calculate the right thing. So it's the solution the network typically finds uses all the units that it has in a kind of smeared, distributed way. The simplest example to think about is if you have an output and you have, let's say we're trying to teach the network just an OR. Well, we know that we can do OR without any intermediate units. Right? So if we didn't have that, we could connect this directly to the output, it will learn OR perfectly well. But suppose we did give it 3 intermediate units. Each one of them would kind of learn on its own to do an OR. Or something related to an OR. But a combination. So if there's redundancy in the network just smears the solution over the entire redundancy. So back to your question. If you have too few units, you won't be able to reduce the training error. If you have too many units, you will learn a solution very quickly. But, as was pointed out, remind me of your name? Doug. As Doug pointed out, the solution will not necessarily be meaningful, in the sense that you did not force a network to find a compact calculation, a compact representation of the relationship between the input and output. So it is free to memorize the input. Of course, it depends on how many input examples you have. But in the case of 8 input examples, and going from an 8 to 100 to an 8, it is very easy for the network to effectively memorize the memorization is encoded in the weights, but it's memorization nonetheless. And when you memorize a solution, you don't generalize it. Right? If I told you 2 goes to 4, 5 goes to 10, 17 goes to 34, 9 goes to 18, and 15 goes to 30. Okay? If you have very good memory, you don't need to understand anything. You can repeat that back to me. And then I tell you, what does 6 go to? And you have no idea. But if you have very bad memory, and I'm still forcing you to be able to spit back these 5 examples to me, but at least I give you you don't have to spit back the entire input-output. I give you the input, you have to spit back the correct output. Now you have, I don't know, very little writing space, and you have to write something to remind you. If you discover the rule that is just multiply by 2, you can do that, and now you can do other examples too. But if I give you a huge piece of paper and you just write down the 5 training examples, you didn't learn anything, you memorized. So, giving the network too much freedom, too much representational power will push it towards memorizing. And that's, I think, what Doug meant by not a meaningful solution. It's a memorization solution. It's a rote learning solution. Whereas giving it just the right bottleneck forces it to find a meaningful, compact explanation of the relationship between the input and the output, assuming one exists. Okay? If your input-output is produced by some random process and there's no relationship between the input and output, and you're trying to force it through a narrow network, you will never find a decent solution. Please.
So, in practice, do they just guess a topology and keep reducing the number of nodes for training?
That would be a very reasonable thing to do. So, instead of keep reducing, I'd rather start from small and grow, because it takes less CPU to train a small network than a large network. So I would guess at the topology, and then I would start with a network that's quite small, knowing full well that I may not be able to reduce the error rate, the training set error rate, and try and try and try. If I kind of say, okay, let me add another hidden unit and try again, and grow it until I can do it.
Is it necessary to retrain the whole thing, or just add another hidden unit and maybe like give it more examples, and then maybe the weights change a little bit more?
That's a very good idea. Training a neural network is very computationally expensive. You already trained a big network, you want to add one more unit to the topology. You could start from scratch, or you could just add this unit and start from the weights that were already there. And the only thing that's new is the weights that connect this unit. I think it's a very good thing to do. One could argue that it's suboptimal in some sense, but on the other hand, even if you start from scratch, you're not guaranteed to reach global minimum, right? So it's a heuristic, and you could argue actually it's a very good heuristic, because you're starting from a place that's already known to be pretty good. But on the other hand, the other hidden units have already, in a way, committed themselves to performing a certain function. So you're already pushed into a part of the solution space where different people know what they're doing. It's a little bit like you come into a company and you're an additional member of the team, and everybody's already know what they're doing and they have a certain way of doing things, and you have to find a way for you to fit in and to add to the overall output, which is fine. The alternative is to pull everybody from their job and reassign everything to everybody, and yes, you may be able to find a more productive solution, but then again you might not. So it's all heuristically based. It's a very reasonable heuristic. Other comments? Okay, well, you guys asked all the right questions. So we're going to switch gears now and move to chapter 7, which is the most mathematical chapter in the book. So chapter 7 is about computational learning theory. It's a much newer field than machine learning as a whole. Machine learning as a whole you can think of as a field from the 70s, maybe. Although some of the ideas, of course, come from statistics, which is much older. Computational learning theory has only become a significant subfield in the mid-80s. The idea of computational learning theory is to try to prove theorems and properties of specific learning algorithms and also of specific classes of problems. What functions are learnable and what functions are not learnable. If functions are learnable, how many examples do you need in order to learn them? Can you guarantee under some conditions that if you have at least this many examples, you will learn the function correctly? Can you guarantee that if you have no more than this many examples, you're not able to learn the function? These are the kind of questions that you're trying to answer. So it's the intrinsic properties of classes of functions that you're trying to learn, and of classes of algorithms, and of the dependence of that on the number of training examples that you have, or that you need, and the amount of computation, or I should say computational resources, both time and space, that you might need. It is useful to break down computational learning theory to several different settings. Let me put it on the board. Thank you. Okay, so these are the three settings we're going to talk about. First setting is when the learner, in our case the algorithm, poses queries to the teacher. Namely, when you might have a set of training examples already and you have the ability to get more, and it's up to the algorithm to decide which input to present, and then there's a teacher that gives you the right output, the right answer. As you might imagine, this is a very powerful paradigm to be in from the point of view of the learner, because you can choose the most informative questions to ask. Do you remember we mentioned, I think we mentioned here the 20 question game? So when we talked about version spaces and we said you have a version space, now you're free to choose a question. Which question will you choose? The answer was you choose a question for which half of the hypothesis in your version space give one answer and half give another answer. And in information theory terminology, you choose the most informative question, the question whose answer has the most mutual information with the correct hypothesis, or reduces the entropy of the version space the most. Another setting is when the teacher chooses the examples. This might actually be better in some situations. One advantage the teacher has is that they know where they're trying to take you. They know what concept they're trying to teach you. One advantage you have as a learner is that you know what you know and what you don't know. Okay? So there's this difference between what information is available to the teacher and what information is available to the learner. Each have part of the information. The teacher knows where you want to go to. The learner knows where you are now, what your current state of understanding is. And sometimes it makes more sense to let the teacher choose, sometimes it makes more sense to let the learner choose. And then the third setting is where instances are not chosen judiciously, but are generated randomly from some underlying distribution. So there's an underlying, presumably fixed distribution over the input space, and you push a button, you get one sample, one independently drawn sample from that space, and then the teacher just labels it, puts the correct answer on it. But the input is chosen randomly, the output is provided by the teacher. Each one of these settings leads to a totally different kind of analysis. Okay, question. In 6th grade arithmetic class, the teacher is teaching the students how to do long division. I think that's 5th grade actually. Which of these three settings is that?
Setting 2.
Setting 2. Teacher chooses examples. Yeah, I would agree. I mean, yeah, the teacher could ask the students, but typically they don't. They choose the examples. Okay. Different situation now. You're a biologist working in the wet lab, and you're trying to figure out the mechanism of virus entry into a cell, and you can do experiments. Which setting are you in?
Setting 1.
Yeah, I think you're in setting 1. In fact, the entire sort of scientific process is setting 1 in a way. What science is all about is asking the right questions and doing the experiment, getting the answer, and then eventually figuring out the explanation. But typically the scientist is free to choose what experiments to do. So in a way they're choosing what questions to pose to nature, and nature, being the teacher, just gives the answer. The third setting is actually the one that's most commonly used in machine learning, and it's actually very commonly encountered in everyday life. So an example of that would be you're trying to build the next big Google, the next best search engine, and there are search queries coming in. Don't think about them as queries, just think about them as challenges to you to show how good your search engine is. You have no control over them. There's a certain distribution of them, and you may have a teacher, you may not have a teacher, but you're trying to do the best you can with examples that are chosen from you by not by nature in this case, by society, but are outside your control. Or in the case of Enjoy Sport, if you're applying you're trying to learn from the next 7 days, you have no control about what the weather will be in the next 7 days. So you take what you get. You can use these 3 settings to answer any one of the questions I posed before. So let's take the question of sample complexity. Namely, how many training examples are needed in order to converge on the right answer? The answer may be very different under these 3 settings. And let me give you very concrete examples. We already said that for the first setting, when the learner poses queries, a good strategy is a 20-question game. Is choose a question that cuts the hypothesis space in half. So how many questions would you need to ask to bring down the hypothesis space to a single hypothesis, to shrink everything down to one answer? If every time you cut it in half, the answer is you need log base 2 of the size of the hypothesis space, right? Now compare that to scenario 2. There's a teacher who knows the target concept, and they provide you with training examples that are tailored to help you reach your answer as fast as possible. So how many examples will you need depends, of course, on what the target function is. But let's take a very specific case where the hypothesis space is a conjunction of up to n booleans. Do it here. H is the set of all conjunctions of up to n Boolean variables for their negation. Let me explain what I mean by that. Example, one function that is in H would be x1 and x3 and not x6. So x is a boolean, 1 or 0. This example is in the book, by the way. And any function can be expressed as a conjunction, as an AND, of any subset of the variable up to n, such that every variable occurs either by itself or with a negation or doesn't occur. How big is H, by the way? How many hypotheses are in H defined this way? Sorry?
2 to the n.
2 to the n? 3 to the n? Any other answers? Do I hear 4 to the n? Why 3?
Well, a variable can either be there, not there, or not.
Right. Every variable can either be there by itself, be there with a cross, with a bar, negation bar on top of it, or not be there at all.